So the next talk is by Jim Phillips from the Theoretical and Computational Biophysics Group. This is one of our oldest collaborations, and Jim will talk about recent advances in NAMD.
Okay, so thank you very much. And I'm Jim Phillips. I'm the lead research programmer for our molecular dynamics code NAMD for quite a while now, and it's been a good year. So this is the HIV capsid simulation that we've gotten a lot of press on. The man largely responsible is Juan Perea, sitting here in the middle of the room, sort of hunkered down. And like I said, this went very well. So HIV is everyone's heard of HIV. It seems important, but why is this work really interesting? So just to let you know what's going on here, this is sort of how the HIV virus is put together. You've got the capsid, which is this protein shell, and then outside the capsid, there's another protein shell, then there's a membrane, and then the membrane has various proteins in it to fool the cell into thinking, okay, this is something that you want to let in. The way the infective cycle actually works is we have our little viruses here, so they have to bind to the cell, they have to fuse with the membrane, inject the capsid, and then the DNA, RNA from the virus has to be reverse transcribed and has to sort of infect the cell, take over the cell. You need to reproduce, more viruses on the way out to continue the cycle. And there are a couple small details that the capsid is responsible for. It's uncoding and actually getting into the virus. And I sort of want to explain, when you think of this capsid, yes, if you look at the picture, it's a big clump of proteins, but it's actually a very specialized structure. So I like to use a soda can as an example here. So if you think of this, there are lots of things you can put soda in. Why do we use this? Well, first of all, it's designed to not open randomly, so you can transport this all over the country, it doesn't leak. When you do want to get something out in the right environment, in the hands of the user, well, first of all, it looks like something that you want to drink. It looks appetizing. It doesn't, list the, the poisonous contents in large print. It's, Diet Mountain Dew. When it does get to the right environment, it opens easily. It dispenses the contents to the right part, onto your tongue, not, down the front of your shirt or onto the floor. When you first open it, it sends out a nice spray. It smells good. It sounds good. It hits the right part of your tongue. And then, to make more of them, it's very efficient in terms of materials to be able to put something this together easily and recycle it. So the capsid is not just a container. It's an active part of the infectious cycle here. In particular, as I said, it plays a role in, it has to fall apart at the right time, and it actually plays a role in actually putting the RNA into the cell. How do we fight HIV today? Well, we've got drugs that try to prevent basically the virus membrane from fusing with the cell membrane. We have drugs that try to impede reverse transcription. The reason that these are called retroviruses is that the viral RNA is transcribed into DNA, which then goes into the nucleus of the cell rather than simply sending out RNA directly. Integration into the host genome, and we have drugs that try to prevent protease that breaks off the new viruses. We have nothing currently that targets capsid uncoding or nuclear import. So having the structure of this virus really makes it possible to potentially develop drugs or understand what drugs might do when they interact with that. And so the question is, will targeting the capsid create the most effective drugs? So the short version of that answer was that, first of all, since there are no drugs that target the capsid, there's no resistance to a class of drugs that target the target. And second, in nature, simians are immune to HIV. And the way that is achieved is that they actually have proteins which interfere with the capsid somehow. So it is a promising domain. Okay, so work like this, of course, takes a village. So we work right across the way here at the Beckman Institute. This is sort of Schultenville. And we have two main packages, a visualization package, VMD, and the simulation package, NAMD. Large number of collaborators, long history as a NIH-funded resource, which we hope will continue for some time going forward. one of some of the things that we have locally, we can't afford, our own supercomputer, but we have been assembling the infrastructure to be able to manipulate these kinds of simulations. So yes, we've got Titan or Blue Waters here. We need to store the trajectory. We need to analyze the trajectory. We need to be able to visualize this kind of thing. Now the problem is we can do this, but we're supposed to make this software available to outside groups. We let them come in and use this, but the direction that we really need to go, and I'm telling you because my hobby this year is telling everyone, we need to virtualize this infrastructure. So instead of making people get their own hardware, we have, the large-scale compute, we have storage, we need large memory analysis style computation, and more importantly, we need remote visualization capability integrated with the supercomputer sites so that rather than sending, needing a 10 gigabit link just to download the data, store it somewhere, all the work we've had to do, you just send compressed video just like you watch Netflix today, only slightly, higher resolution. So that's the goal right now. Texas is actually leading on the way on this. So the Stampede cluster has nodes that have a terabyte of memory. It's not, virtualization like is being worked on, but you basically allocate an entire node. It just works. They've got the new Maverick cluster. Blue Waters doesn't have a visualization resource. Titan nominally has one, but the new cluster they added doesn't even have GPUs on it. So that's not going in the right direction from our viewpoint. And I realize that there's maybe one person who does the molecular visualization in the room, but just performance analysis on this class of machine, doing the traces that you get out of projections and viewing those, this is a large memory workstation with an SSD RAID that I transfer the files onto, load them onto, and then I'm looking at it on this 4K display. It's really nice to be able to run the job, leave the traces on the parallel file system, and just load them directly when working on Stampede. So that's my little goal for the year, is to actually get some remote visualization resources onto Blue Waters. But so as we said, NAMD, we have to serve a large number of people. So the goals that we've had is that, these are biologists, biochemists, biophysicists that we're serving. They don't need to understand how the program, well, it's not the laser, how the work program works internally. We try to support, everything from desktops, so we teach workshops. You can come, learn things there, go from that to your local cluster, campus cluster, to the largest supercomputer in the world, and really not even know what Charm++ is. So we try to preserve that, and it's available free of charge. So we've also moved up the scale. Over time, this is what we've sort of been doing. Machines have gotten larger, the software's gotten more capable. We've gone from sort of single proteins to small protein lipid complexes. This is ATP synthase. This is a little ratcheting thing that stores chemical energy in the cell. This was the first virus we did back in 2006, satellite tobacco mosaic virus. It's a virus, but it can only infect the cell that's already infected by another virus. So the tobacco mosaic virus is sort of the main virus, and if you've got that, well, then this virus piggybacks on another virus. The ribosome is the structure that reads your DNA or reads your messenger RNA and churns out proteins. If we can understand how this works, we can, this is different between bacteria and eukaryotes. So if we can understand how this works, this is what a lot of antibiotics target. And then finally, the HIV capsid. This was a 64 million atom simulation, the current thing. But what I want to point out here is that we're not doing larger simulations just because we can do larger simulations. We're not taking, 1 protein, 10 proteins, 1,000, 1,000,000 proteins. There's one of each of these things in here. And this is not a symmetric structure. You can't model, this one corner here and represent the behavior of the entire structure. This is asymmetric. You nearly need to do the entire thing to understand the mechanism, understand the dynamics, understand how this falls apart, understand how this operates within the cell. So we're not doing big because we can do big. We're doing big because biology is getting big, and this is the level of experimental data that's coming in. Okay, so back 2006, again, this was the first simulation. We actually learned something from this back then. If you take the RNA out, the thing collapses on its own. HIV, it's actually stable without it. People say, well, Why do you have to do every atom? Why don't you do coarse graining? Well, we have done coarse graining, and you can do some things from coarse graining, but it's not that same. Life is basically put together atom by atom. Some things you have to understand the entire structure, and once you understand the entire structure and you understand the mechanisms, then in some cases you can put together a coarse grain model that lets you go to longer time scales more cheaply. But it's not a substitute. This is where we were back in 2006 when we first found out that NSF was going to be building this large-scale supercomputer that eventually became Blue Waters. So this was on Big Ben, which was running up to about 3,000 cores. They were single-core processors back in the day. So this isn't ambiguous down here. And here's the virus and the ribosome scaling up to pretty much that whole machine. It's been a long, strange trip. This is where we've gotten to now. So this is running on Titan in red, Blue Waters in blue, and the Mira Blue Gene Q up at Argonne in black. Note this is number of nodes. Titan and Blue Waters are sort of our main production platforms. I actually had to get some emergency access from Benoit Roux to even run these benchmarks on Blue Gene Q, but it works very well. It's easy to scale well when your processors are slow and your network is fast. But yeah, we've put a lot of work in this, and we're basically getting up to, this is a 224 million atom system, so this is over twice the size of the Blue Waters acceptance test, 3-4 times HIV, running up to effectively the entire machine. These are nodes, not cores. 14 nanoseconds per day, 80% parallel efficiency, which is really great. Smaller systems, we can go faster, not using the entire machine, and then we get a pretty decent boost out of the GPUs. But as you scale up, you lose some of the you lose some of that to the network. But the GPU version is still always faster. So yeah, and of course we owe a lot to Professor Calais and the Charm++ group. This is recognized. Professor Schulten and Professor Calais actually shared a Fernbach Award 2 years ago. And this has really been synergistic research. So, there were requirements in NAMD which inform Charm++. Charm++ develops features based on those. We already have working features that do the same thing, so we ignore that for about 10 years or so. And eventually, after we believe it works, then we start filtering some of those things in. But really, there's a lot of back and forth. And also, as you've seen, the software works at scale for very challenging problems. So we use Charm++ basically as a parallel C++ with data-driven objects, asynchronous method invocation, prioritized scheduling of messages and execution is important for performance, measurement-based load balancing, and again, as a portable messaging layer, being able to optimize better than MPI for the Cray and the IBM networks. The design in NAMD goes back quite a ways, and it was evolutionary or revolutionary and somewhat underappreciated at the time that we have these spatial domains and sort of independently separate the decomposition. So it's not purely a spatial decomposition, it's a hybrid space and work-based decomposition. The data domains pretty much stay put, but we can dynamically load balance the work. And then overlapping execution. So during a time step, we have sort of these bonded terms that represent covalent bonds, the non-bonded terms, which are pairwise, and then long-range electrostatics is implemented through particle mesh AWOLD, which is a fast Fourier transform-based method of doing long-range electrostatics. This is the latency limiting stage, so this is shown as a two-dimensional slab or one-dimensional slab decomposition with a single transpose for larger systems. We use a two-dimensional pencil decomposition that has 4 transposes, z to y to x to y to z, to do this calculation. And we can overlap this, and this all hides. When GPUs came around, the pairwise objects are by far the most expensive part, so we offload that to the GPU. We were sort of early adopters for this, and we can overlap communication and computation on the GPU with the CPU, transferring positions, running some of the forces in parallel, doing the local forces last so that we can communicate forces and positions. This is the actual timelines from what's going on there. Again, position transfers, upload to the GPU, run on the GPU, transfer the forces back. and then receive the local forces locally and continue immediately with integration. Okay, so getting from the million atom virus to 100 million atoms was really pretty challenging. Just the million atom simulation, when we did that for the first time, it was sort of a natural extension of the tools that we had. It fit within the memory of the machines. Runs a little bit, it ran slower for some parts, reading the file, but it pretty much just works. To get to 100 million atoms, we had to fix a lot of things. We have new file formats. The molecular structure doesn't fit in a single node's memory anymore, even in SMP mode, which we were already doing, so we have to distribute and compress that. Input data, shared memory, lots of change there. We also had to put together the benchmark that was supposed to run on this because it was specified as a rather vague paragraph. So that's just for 100 million atoms. Then getting up to 300,000 cores on Blue Waters, Turing++ shared memory, tuned for Power 7. They changed the machine from Power 7 to Cray, tuned for the Cray network. Replicas to be able to do different simulations for smaller things, optimization for physical nodes in the machine, a whole lot of stuff. Plus, oh yeah, they wanted, we need to run on GPUs. So lots of work goes into this. Some of the more recent work, I just want to highlight adapting to the Torus topology of the network. It's relatively simple-minded, but it made a pretty big difference in some cases. When you run on a blue gene, you sort of get this irregular Torus network. So if you imagine here, you've got gaps in it. It's not like a blue gene. You might have other nodes running at the same time. The first thing we do, we take the nodes we're assigned, we rewrap that to the most compressed set. So you might be, big gaps in the middle. We rewrap that. Then we just sort of do a recursive bisection, both on the nodes that we're given. So we'll take this curve through the nodes, divide in half, and then in the next direction we'll go the next longest direction. We do this to both the torus of the machine and to the patches that are in the simulation, and pair those up. And that gives us a good mapping between the structure. We have minimal work that's on each physical node, and then we pair this up, and it makes a pretty good difference. So running on Titan at the largest scale of the machine, we actually see a 50% performance increase from doing that over sort of what the machine default node ordering is. What we had found before this was the Turing++ node ordering is if we just sort of have the nodes sorted along one dimension rather than the space filling curve that the Cray seems to use by default. We can make that worse, and if you want it to be even worse, if we just sort of totally randomize the topology and the node ordering of the machine. So on the Cray XK7 network, topology definitely makes a difference, and we can make it better and we can make it worse. So we know now how to make it better. So this was a nice improvement. Again, as you get smaller, it doesn't matter as much unless you consciously try to make things worse. One note for those benchmarks, when you do runs on these platforms, you get great variation in your performance from run to run. Particularly, you might get different allocations, so you might have different shapes, different parts of the machine. There are other jobs that are using your links, so you can't just sort of run once, case A, then submit another job for case B and keep comparing. You really have to run everything back to back in the same job on the same allocation to really get comparisons. So that's what we had to do, which makes these studies a little more expensive. Blue Gene Q is a 5-dimensional torus. Makes absolutely no difference what we do with the torus, with the topology on that machine. It's exactly the same. So, well, topology may have been a little bit more important on L and Q class machine, L and P class machines for NAMD. For Blue Gene Q, we're not seeing that much of an effect at all, which is really a strength of the network. So the CUDA kernel, so PME, I mentioned before that for particle mesh AWOL, we've been doing that on the CPU and only offloading the non-bonded. When we went to the 100 million atom simulations, the PME communication and FFT really became a bottleneck. And sort of the breakthrough for that was realizing, well, we're using this sort of standard fourth order interpolation, so every charge ends up in a 4 by 4 by 4 cube. If we switch that to 8th order interpolation, well, yes, you get 8 by 8 by 8, which is a factor of 8 more points for each charge, so that work goes up, but you can cut the size of the grid in half, so you have a factor of 8 less data that actually has to go across the network. So that's actually a big improvement on that critical path. When you do that, you're putting more work into doing that gridding and ungridding. So if you offload the most expensive part to the network, that can still be significant. And in particular, we're offloading. You want to get the data on the network as fast as possible, so we can feed that up. So we put together sort of very, basic Kepler optimized kernel for doing that. The first time we tried it, it was actually slower than just doing the PME on the CPU completely. Initial plan was, okay, for every patch, we'll submit a CUDA kernel. Those kernels can run on the entire machine and get back. There's just too much latency on the GPU to be able to launch that. So okay, we fixed that. So instead of 1 per patch, it's 1 per PE. Now we're launching, 8, 10, 12 kernels per step to do this. Still not quite faster. Then we realized, okay, this is all running on the same GPU. We can sum everything into the same charge array, and that's actually faster. And part of the reason for that may simply be that we're also sending fewer messages per node. So rather than having each PE on the node sending its data to the corresponding grid locations for the FFT, we're sending one message per node to those grid locations. So that is a potential source of the optimization that we can now backport to the CPU version. What we actually get out of that, so I mentioned coarsening the grid and doing higher order interpolation. This is how much you lose by turning off various optimizations. We turn that off, we drop by a factor of 2. If we don't offload to the GPU, we drop by about 20%. So this was the big improvement, was actually getting to that coarser grid. Then you get a small boost from offloading the interpolation to the GPU, and about a 10% boost from reducing some synchronization in the constant pressure integration algorithm. So what did we learn from all this? So basically, the lesson is that optimizing communication is job one. In particular, this is sort of a new pet peeve of mine. There are lots of things where, okay, I need to write a broadcast tree. Well, if I 0 sends to 1 and 2, 1 sends to 3 and 4, 2 sends to 5 and 6, this n to 2n plus 1, 2n plus 2 pattern. If your nodes are arranged at all sanely, this is sort of the worst possible thing that you can do. Because first of all, most of the first stages of broadcasting are all within a single node. And then everybody on that node is sending the same message multiple times to other nodes. And even worse, if you look at the topology of the machine, you're sort of broadcasting on the left half of the machine, spreading out, and then the entire left half of the machine sends to the entire right half of the machine. So if you instead send far away first and do the broader stage of the tree locally, the way that you would normally write a tree, works much better. And this, things like this were actually causing the network on the Cray to throttle, which is when the network freaks out because there are too many messages and says, okay, nobody sends anything more than a single node can process until we drain the network. And then you sort of find out after your job is run that this happens. So very bad. Other than that, basically avoid sending messages unnecessarily between different physical nodes in the machine. Within a physical node is not as bad. Ideally, sending data within a node is virtually free. And again, doing that. As far as lessons learned, otherwise, incremental development is entirely possible. You don't have to rewrite the entire machine. You want to go from working code to working code. Memory issues you can fix as they arrive. Definitely use profiling. Profiling will tell you what the problem is, but it won't tell you what the solution is. It was really sort of insight that led us to the PME and load balancing issues. Be careful about major rewrites. You really need to understand what you're doing before you want to put in that kind of effort. As far as Charm++ goes, I was sort of gratified to see that other talks today have had a similar lessons going on, similar types of things. The programming orientation really needs to switch from thinking about PEs to actually thinking about nodes. So thinking about programming the entire memory space. For one thing, you have shared data that you really want to share at the node level rather than distributing at the PE level. Lots of codes do that. Parallel I/O, you want to distribute that across nodes and physical nodes. You have various offloading processors such as GPUs or mic processors. Those really have to be managed at the node level. You can't multiplex things from every host thread onto these. Dynamic load balancing with a node should be pretty much free. And finally, the change that I'm looking for is to be able to have array elements rather than being mapped to specific PEs, able to process entry points at any PE in the node. So we have node groups now, node arrays. Finally, one thing that I've also noticed people doing is like, well, we need better support for execution fences. So there are lots of cases where, if we start X, it's going to lay Y because X has some long-running elements. So we need to add fences so we don't start X on the PE or on the node until all of such and such from this phase has happened to avoid delaying it. So we do this for computes. Don't launch any computes until all the patches are ready. Don't launch any computes until all the proxies are ready. Don't start the GPU non-bonded work until you've launched the PME work. One property is these are pretty much exclusively used for performance reasons, not for correctness. So people write the code, that allows these, they observe this is happening, then they fix the performance issue. Features like this would also enable MPI-style sequential programming. Okay, so thank you very much to many people. And again, Juan, responsible for the HIV work, is in the room, and I assume he's going to lunch. So if you have any questions for him or for me, thank you.
Thanks, Jim.
We'll get you a microphone. So the question was sort of, how does the free world of the science and the software mesh with actually developing HIV treatment?
So we work with, these are 3 big collaborations that are funded by NIH. Some of them have collaborations with pharmaceuticals like Pfizer and Boehringer Ingelheim. So there is like an ongoing effort to develop new drugs, and we're part of that. It's a collective effort. It's pretty big, actually. They put on resources, they put scientists, they put good sense of that. Oh, I think this is more general than.
Yeah, there are layers and layers in this collaboration, from the experimental groups down to the scientists who are running the simulations, to the developers for the software, all the way to LA. So it's yeah. Well, this is just for NAMD. I mean, I've got a whole other slide somewhere for the. See if I can find that. Yeah. So this is sort of the direct HIV acknowledgement. So we've got the local work, excluding lots of people locally who have helped with this, and the whole NAMD team, and then the different experimental teams that contributed to the Nature paper.